Now let's continue with the method of partial fractions. So before we were doing the assumptions of the partial fraction, where we have a function that can be seen as two rational functions, p over q of x, where the degree of p is less than the degree of q, p and q being polynomials. We had a couple of cases that we explored before. We explored the case where we have distinct linear factors. We explored the case where we have a product of linear factors, which are repeated, and now we're going to explore the third case, which is when we have a irreducible quadratic factor, none of which will be repeated, and then we'll explore the case where we contain repeated irreducible quadratic factors. So case 3 is where q has the factor of the form ax squared plus bx plus c, but that is an irreducible polynomial. What do I mean by that? Well, it means that when I'm getting the quadratic formula to get the solution, we're going to have this term, b squared minus 4ac, to be negative. So that means that we're going to have negative roots, or we're going to have complex numbers in the roots. So this is what we call an irreducible factor. And so when this happens, what happens is that the partial fraction that we're going to construct, or the term for this particular factor, is going to be from the shape ax plus b divided by ax squared plus bx plus c. So essentially we're going to keep it in this form. And we're going to determine again what a and b are before we continue with the integration. Now let's see some examples of this in use. So first, we're going to go with 1 over x squared plus 1, dx. And so again, the x squared plus 1 factor is an irreducible term, because the solutions with this is equal 0 will be the number I, which is the square root of minus 1. So this factor is going to be an irreducible. So if we want to arrange the partial fractions here, this is going to have the following shape. It's going to be a over x in bx plus c over x squared plus c plus 1. Sorry. Now, once that we get to this point, the procedure is exactly the same. We multiply this to the other side, and we're going to get 1 is equals a x squared plus 1, and then plus b x plus c times x. And so we start by giving values that we know that are going to give me an easy constant. So if x is equals 0, notice that I get 1 is equals a, and that's pretty much it, because this is 0 plus 1 is 1, and this goes to 0. So with that, I got a out of the way. Now let's try with x equals 1. So this is 1, and a is equals 1 as well. So this is going to be 2 over here plus, and then this is going to be b plus c times 1. So this is going to produce an equation. Notice that this is going to be, I'm going to move this 2 to the other side, and it's going to be minus 1 is equals to b plus c. Now I want to use another number, x equals minus 1. And if I use x equals minus 1, I'm going to have that 1 is equals to a times 2 plus minus b plus c times minus 1. And then again, a is equals 1. So we can change that a little bit here. This is 2. And then multiplying by this minus, I'm going to have here b minus c. And so simplifying, this is minus 1 is equals b minus c. So now notice that I have a system of equation. It tells me minus 1 is b plus c, and I also have that minus 1 is b minus c. So likely this means that c is going to be 0. This is the only way that this is happening. This b plus c is -1, b minus c is -1. So this will implies that b is -1 and that c is equal 0. Of course, you can solve this system of equations and find that out. If you add these two equations, you're going to have that 2b is equals -2, and so that means that b is equals -1. And so doing that, you're going to find out that c is equals 0. So with that now under the belt, then we can just rearrange our integral. And this is going to be the integral of 1 over x dx plus, and then we're going to have minus x over x squared dx. And notice that this is going to be something that we can do with a substitution. This one, if this first one is log of absolute value of x, and this one is going to be minus, and if we use u equals x squared plus 1, then the du is going to be 2x, so we're going to get a 1/2 here. So this is going to be minus 1/2 log of x squared plus 1 plus c. And that's it. This is the procedure that we follow for when we have this particular irreducible terms. Now let's check another example. So now we have the integral of 4x squared minus 3x plus 2 over 4x squared minus 4x plus 3 dx. Of course, then this is, they have the same power, so we gotta do long division first. And if we do long division, we do 4x squared minus 3x plus 2 divided by 4x squared minus 4x plus 3. Long division is just going to be 1 plus x minus 1 over 4x squared minus 4x plus 3. Notice that because they have the same degree, it's normal that this here is a constant. Now over here, then we have now that the top has lesser degree than the bottom, so we can do partial fractions with this one. Of course, normally what happens is that you try to factor this out, but notice that if this is a, b, and c, then we check that b squared minus 4ac is what? This is 4 squared minus 4 times a, which is also 4, by c, which is 3. So this part is clearly bigger than this one, so this is going to be less than 0. And so this tells me that this is an irreducible term. So when I'm doing partial fraction for x minus 1 over 4x squared minus 4x plus 3, then I know that that's just going to be an irreducible factor. And then this is going to be from the shape ax plus b over 4x squared minus 4x plus 3. And I'm probably going to be able to find what this factor means, but it's easier if I try and factor this out, because I'm probably going to need to make a substitution later. So one way that I do this is completing the square. Notice that this term here is like a 4. So if I factor, then I'm going to introduce, this is x squared minus x. And so if I complete the square, remember, it's essentially divide this number by 2 and a square here. So this will be 1 divided by 2. And so if I square that here, this is going to be 1 over 4. But because I'm adding 1 over 4, I'm also subtracting 1 over 4. Now, I want to get rid of this part that is not inside, so I'm going to multiply back again. So this is going to be 4x squared minus 4x plus 1, and then minus 1 plus 3. And so notice that this minus 1 is going to fall with this 3, so ax plus b. And I gotta fold this one in a binomial square. This is 2x minus 1 square, perfect square from this part, and then plus 2. And so now I have a term that is much more easier to arrange and to manage, and even for substitution to work with. Now, with that, then I gotta find out what the constants are for this particular example. And the procedure that we follow is exactly the same thing. So notice that I don't have anything greater here, or I don't, if I'm comparing this with this, I clearly can see that that a is equals 1 and b is equals minus 1. That's just the values that I'm going to have. So I don't need to do anything special in here. And I just realized, oh, so this means that this is just going to be x minus 1, 2x minus 1 squared plus 2. This is the case in this scenario because I don't have another factor in my multiplication. If I have another factor, then I probably gotta find out what the constants are. But now, once that I have this, then this is a much more easier or manageable integral to do. So if I could go back here, there's gonna be the integral of 1 dx plus x minus 1 over 2x minus 1 squared plus 2 dx. And of course this is x, and now I'm going to do here substitution. It's very easy to change this to be a substitution where u is 2x minus 1, and so the du is the 2 dx. So this is going to give me a 1/2 out. And this bottom is going to become u squared plus 2. And now the top, I got to find out what x is. So from here, u minus 1 over 2 is just x. So that's what I replace over here. This is like 1/2 u minus 1. Let me just rewrite this. One half u minus 1 minus 1, the u. And so notice that I can arrange this to be just simplifying x plus 1 over 4 integral of u minus 1 u squared plus 2 du. This integral by itself is proven to be a little bit more cumbersome. So let me separate this part. This will be x plus 1 over 4, and it's much more easier to separate this to pieces, u over u squared plus 2, that I can do with a substitution, and then this minus 1 over 4 1 over u squared plus 2 that I can do also with a trig substitution. And so by the trig substitution, of course I'm talking about tangent. Notice that this is very close to tangent to the minus 1. So this is going to be x plus 1 over 4 and then the log of u squared plus 2. That's what I get from here. Actually 1/8, because there's a 2 that comes out from the substitution when I'm integrating this log. And from here, same thing. This 2 is like a square root of 2 squared. So I'm gonna get a 1/square root of 2 out. So this is gonna be 1/4 square root of 2, and this is gonna be arctangent of u/square root of 2. And then, of course, getting back to the original variable, this is x plus 1/8 log of 2x minus 1 squared plus 2 minus 1/4 square root of arctangent of 2x minus 1 over square root of 2, and then plus c. So this could be a very cumbersome and long integral if we have something more than this going on in here. So this is a good example of a complicated integral that we get to transform into a far easier one if we get the right arrangements. Of course, now we have left the last case, which is when we have repeated terms of this nature. So we'll see that in the next video.